What's up? If you've spent any serious time as a computer analyst, you know the drill. We're completely accustomed to the legacy storage architectures we've relied on for literal decades. You know, the Microsoft-engineered FAT32 and NTFS systems. But welcome to today's explainer, because we're absolutely not talking about some minor incremental software update. We're unpacking a highly experimental architecture known as the VERTEX filing system. This is a system that literally rewrites the lowest level math of computing to pull off something entirely unheard of in traditional data storage.
And it all comes down to this absolutely staggering number, 10. The core documentation for the VERTEX system claims a downright mind-blowing 10x storage efficiency. Now, if you're familiar with those traditional block-based filing systems created by Microsoft that have dominated our hard drives forever, you know a 10x jump isn't an optimization. No, it's a complete paradigm shift. We're talking about doing fundamentally more with the exact same physical hardware. So how on earth does it actually pull this off? Let's check out its arsenal.
These right here are the 4 foundational pillars of the VERTEX matrix. Basically, instead of writing data into rigid, fixed blocks like older Microsoft filing systems do, it uses arbitrary bit-level storage. And because of that, it achieves zero slack space, which means, literally, 100% utilization of the drive space. It pulls this off using balanced ternary encoding, and then locks the whole thing down with a heavy-duty security protocol called dimensional isolation.
Here is our initialization protocol for today's explainer. First up, the VERTEX system unveiled. Number 2, beyond binary. Enter trits. Third, arbitrary bit-level storage. Fourth, dimensional security and canaries. And finally, system diagnostics and defragmentation.
Okay, let's jump right into Section 1, the VERTEX system unveiled, booting the fractal ternary matrix. Right there in the foundational code comments, we find this exact quote: VERTEX filing system, fractal ternary matrix implementation. As an analyst, the second you read that, you know we aren't dealing with a flat linear file allocation table anymore. This isn't your standard drive setup. We're looking at a fractal matrix. It's a self-replicating, deeply complex structure engineered to house data in a completely non-traditional, highly experimental way.
Moving on to Section 2, beyond binary. Enter trits, rewriting the base code. Let's see how this thing builds its mathematical engine. Since the literal dawn of the computer age, we have relied on bits, zeros and ones, on and off, true and false. But the VERTEX system operates on balanced ternary logic, utilizing a totally different unit called a trit. Instead of 2 states, a trit has 3. -1, which is low, 0, which is mid, and +1, which is high. Within the system's code, this maps perfectly to values of 0, 1, and 2. It introduces an entirely new dimension of computational logic. Because let's face it, traditional systems are trapped in a 2-state binary prison. By introducing that 3rd state, balanced ternary opens up exponentially more combinations within the exact same sequence length. It's basically like increasing the vocabulary a computer can use to store information, without actually increasing the number of letters it has to write down to say it.
And that brings us to the critical math behind this massive efficiency gain, represented by this highly specific number, 1.585. Because we're using base 3 instead of base 2, the code calculates that 1 trit holds approximately 1.585 bits of data. In practical terms, that means just 3 trits can do the work of roughly 5 traditional bits. When you scale that up to massive gigabyte or terabyte files, the compression and density you get are absolutely incredible. Which leads us perfectly into Section 3, arbitrary bit-level storage, eliminating slack space.
You see, the concept of slack space is the ultimate Achilles heel of traditional filing systems like NTFS. They're block-based. Think of those blocks like massive shipping containers. Even if you only have a tiny 1 kilobyte text file to store, you still have to allocate an entire 4 kilobyte container for it. The empty room left over in that container is slack space, and it is entirely wasted storage. VERTEX doesn't use blocks at all. It uses arbitrary bit-level storage. It writes the exact amount of data it needs to, and then it stops, resulting in 0 slack space, 100% utilization. And the system actually continuously proves this to itself mathematically. If you dig into the getStats method built into the architecture, you'll see it tracks both the physical size and the effective size of the data. By cross-referencing the total trits used against the effective byte size of the files, the system monitors its own efficiency ratio in real time. It knows exactly how much space it's saving by avoiding those clunky traditional blocks. Let's shift gears to Section 4,
Dimensional security and canaries, isolating the matrix. Because with an architecture this dense, you have to ask, how do you protect the data? Well, it uses a mil-spec security model called dimensional isolation. When a file is stored, it's not just dumped onto the drive. It's assigned a cryptographic UUID plus a totally unique dimension ID pulled from an incrementing counter. The system then maps out dedicated buffer zones around the data, and within those zones, it places buffer markers at completely randomized intervals of anywhere from 7 to 13 bits. So how does it actually use these markers to protect your files? The system runs a verification protocol. First, it locates the specific file's data buffer. Then, it checks those randomized 7 to 13-bit intervals we just talked about. Finally, at each interval, it takes a tiny 4-byte slice of the data and compares it against an encrypted hex string called a canary. It's essentially a digital tripwire.
If literally anything, or anyone, alters that data, it instantly triggers a system alert, canary mismatch at position X. The split second that 4-byte slice doesn't perfectly match the encrypted canary hex string, the system knows the dimensional isolation of that specific file has been breached. It's an incredibly elegant, low-level way to detect tampering instantly within the matrix.
And finally, let's jump into Section 5, System Diagnostics and Defragmentation, Maintaining the Fractal.
A system this complex doesn't just run itself. It requires some pretty specialized maintenance. The operational toolkit for the VERTEX system features some incredibly robust methods for the analyst. You can call scan anomalies to sweep the entire matrix, or use export metadata for deep debugging. Even a simple delete file command goes beyond just removing a basic index. It specifically scrubs the associated buffer zones so there are no security markers left angling. But for sure, the most vital tool here is the defragmenter.
Because when the console logs defragmenting VERTEX filing system, it is executing a massive reorganization. Look, traditional defragmenting just shuffles rigid blocks around on a spinning disk. But since VERTEX has no block boundaries, the defragment method actively reorganizes individual trits. It pulls the arbitrary bits back together into perfect, contiguous lines to ensure the system remains lightning fast and entirely free of that dreaded slack space.
Which brings us to the ultimate question we have to ask ourselves as we wrap up today's explainer. If balanced ternary logic and arbitrary bit-level storage can genuinely unlock a 10x efficiency gain with absolutely zero wasted slack space, why are our everyday machines still trapped in binary, block-based architectures? The VERTEX filing system proves the math actually works. So the next time you get that annoying hard drive full notification, you really have to ask yourself, is the drive actually full, or is it just speaking the wrong language?